All right, so I'm going to be talking about numeric tricks and the normalization of discrete representations of wave functions and simulation cells that you can make with these discrete representations. Discrete wave functions in space and time, it's basically just a wave function expressed as a set of points, each having a set or discrete increment. And these correspond to position and momentum, and these are plotted against a span of time. In MATLAB, we can discretize a wave function by declaring a set number of points, NPTS, as I guess 200 in this case, to be plotted to describe this wave function. Mathematically, how we normalize a wave function. We know that our particle has to exist somewhere in space. It just doesn't disappear like that. The probability of finding the particle in all of space is 1 then for all t. Normalization will help us calculate the probability of finding the particle in an area of space at any point in time. So this is the condition of that. It just says the probability is 1 across all of space. Here's the code for psi naught, basically translated into equation form. We know we must obey that mathematical condition, so we have to include dx, which is in this case actually a discrete step size of around 0.4 in the calculation for psi naught. So if you notice, I have p sub x and then p sub or p naught there. I mistakenly capitalized that one over there. That one refers to initial momentum. Everyone refers to the probability. If you also know, notice I have sigma naught, and that refers to the initial width of the wave packet to be used in this calculation. This will help us build the probability distribution that defines our wave function over a period of time. So this is what that looks like in a simulation cell after it's normalized and plotted position versus time. There's another axis not shown here, but for our purposes, this is sort of the most important bit. You'll notice that the range of possible positions kind of widens in time. That's kind of what we expect from, I guess, any sort of wave function. What should also be noted as the initial momentum in this, I set it to 2.25, and that's high enough to where this actually makes the function kind of extend. It looks like off screen. It looks like it bounces back. That isn't some strange motion of the particle. That's just because the bounds of the simulation cell are not big enough, and after it reaches the wall, we're still measuring it over the remainder of the course of time, so it has to rebound to 0. The position of the particle did not. It kind of exceeded the maximum boundary position in this case. This is a better way to visualize it. Essentially, you can just see it extending past this simulation cell. All right, questions?
Okay, please join me in thanking Evan. Any questions? I have 2 combined into 1. Are there problems where this passing of wave packet through boundaries is okay and doesn't undermine our results? First part of the question. And second, if it is a bad effect, what can we do against it if we still need to have job done and we want to avoid it? Like, which practical steps can we do to avoid passing of the wave packets through the walls?
We can just increase the boundary space. I guess the size of the cell.
Yes, and
or we can set the initial momentum lower.
Perfect.
Okay. Yep. Your first question was, can you repeat it?
Other classes of problems where passing of the wave packet through boundaries is absolutely okay and doesn't create any problems?
Yeah, you measured or you mentioned something yesterday about, or not yesterday, a couple days ago, in lab about when calculating, or when using calculations to describe like cells, unit cells of polymers that are semiconductive.
Perfect. Yep.
Yeah.
Yep.
Okay.
More questions? If not, let's say I don't want to.